Okay, so now we're going to move full on into effects. So Danel Ahman is going to tell us about handling algebraic effects in a dependently typed setting.
Do you hear me? Is it okay? Okay. So yes, thank you. It's a pleasure to be here. Okay. So we have these two areas which have been well studied in isolation. So on one hand, we have dependent types, which allow us to do both functional programming, but then also very precise logical reasoning inside the same system. But most of that work historically has been in the pure setting, so we don't have side effects around. So there are emerging languages like F star, Idris that support it, but in this talk I'm looking at sort of more foundational questions. On the other side we have somewhat an emerging area of algebraic effects and effect handlers that allows us to do very nice modular generic effectful programming that sort of has nice applications, and I'll mention some of them later on. So this paper is about kind of what happens if we have a language that has both of these features, and essentially what can we do in that setting? Can we do anything better than these two things in isolation, and then how to do it? So regarding the outline, so first of all, I'll start with a brief background story of what are algebraic effects, what are handlers, because I expect that there are still some people that haven't encountered them in practice or in theory. I'll talk a bit about what's the particular kind of dependent type calculus that I'm working in. Then I'll jump ahead into the future for a bit, talk about what exactly can we gain from this combination, and then I'll jump back into the past and then tell you about how to actually make this formal and what's the precise system in which the second bullet point is developed and discussed. So okay, let's start with algebraic effects and handlers. So most of us, well, I think we all know that Eugenio Moggi taught us to use monads to model effects. Then people like Phil Wadler made them popular amongst functional programmers. So this is what we have been using kind of since the early days of Haskell and onwards. A little bit later, Gordon Plotkin and John Power showed us that so most of the monads that Eugenio Moggi introduced as models of effects actually arise from very sort of nice syntactic PL-ish presentations in terms of some operation symbols and some equations. And you should think of the operation symbols as representations of sort of sources of effects, like raising exceptions, getting a value from the store, putting a value to the store, and then the equations as describing some computational behavior. So here is a one example equation from the theory of state, which just says that if I read a value from a location, if I put it back, then that's not observable. So this is sort of one of the 5 equations of that theory. And the algebraic approach is in some way sort of superior to just the monadic approach in the sense that it allows you to easily pick the monad for a particular language, because if you just work in the monadic setting, it might be complicated to choose what's the particular monad. It helps you to model combinations of effects better, and it sort of supports nice way of generic effectful programming via handlers. So the second part of the history part of this talk is, so what are handlers? Plotkin and Pretnar introduced them as a generalization of exception handlers. If you want sort of one key point to this is, what you should bear in mind is that a handler is just essentially a redefinition of operations. So when you think of what an exception handler does, this is what it does. It replaces a caught exception with some other block of code, and after this block of code has finished, it will go on to the continuation afterwards. So they have proven very useful also in practice. They give you very nice ways of implementing stream redirection, state rollbacks, even concurrency in concurrent OCaml, so on. So in the purpose of this talk, I'm going to be looking at sort of this style of presentation of what a combination of handler and the handling construct is. So the components to bear in mind here is that this part in the curly brackets is what we would call a handler. What it does is just maps operation symbols to corresponding terms. So you just redefine the terms. And then this n red down here is the continuation that you run after you have finished handling your computation. And then the computation that we handle is this m here. So denotationally, you would interpret this construct as the unique homomorphism out of the free algebra into the algebra that the handler defines for you. But from a more PL perspective, you can think of it is just essentially as providing you a primitive recursion principle for your effectful computations. So the handling construct up here is usually described using two equations. So first of them just says that if I handle an operation, I am going to pick the corresponding user-defined term, replace the operation with it, and then recursively call the handler in the continuation. And then the second equation says that, if I get to the return values in the computation that I handle, then I'll replace then I'll just call the continuation with a particular value. So that was a sort of two-slide brief intro into handlers. So let's now look at the kind of dependent type setting that I'm working in. It's based on a paper from a few years ago with Neil Gani and Gordon Plotkin, and it's meant to be sort of a nice core calculus for effectful dependent type programming. It's very explicit. It's in the style of call by push value or the enriched effect calculus, so it will make a very clear distinction between values and computations, both at the type level and then the term level. So you have value types. The ... is all of Martin-Löf type theory, so sigma types, pi types, propositional equality, whatnot. And then in addition, you have a type of funcs, and then you have computation types. You have the computations that return values of type A, you have a dependent effectful function space, and then you have this notion of computational sigma types that in that Fossak's paper were important to give a uniform account of type dependency in sequential composition, but for that you have to read that paper. And then you have value terms. It's your usual Martin-Löf type theory terms plus explicit funking construct. You have computation terms, which are mostly usual, so returning values, sequential composition, lambdas, so on. And in addition, you have the introduction and elimination rules for this computational sigma type. And because the sigma type will get eliminated into a pair of value and the computation, you need to make of evaluation context or stack terms or what we call a homomorphism terms in this calculus explicit because you need a certain subclass of computation terms that are guaranteed to behave well and not discard the computation variable or duplicate it arbitrarily. So yes, so that's the calculus that was in the Fossak's 16 paper. So when we are working in the setting of algebraic effects and handlers in this paper, so we're looking at a small variation or extension of it, where we will have a Tarski-style value universe around. So this is for this universe we use for logical reasoning. So it will be closed under sigmas, pi's, the empty type, the unit type. They will be written as the hats over the symbols, but I'm really thinking of them as the logical operators in this talk. It's going to be also extended with this notion of Fibred Algebraic effects, which is sort of a natural dependent type version of algebraic effects, where the operation symbols are now are dependent typed in the sense of the type of output values can depend on the type of input values. So an example is that if you think of the get operation for state, then the values that you store in the state can actually, their types can depend on the particular locations. So this allows you to do that. The language and then the computation terms get extended with the corresponding operations, and the equations between the effect terms that are given in the theory will be translated into definitional equations in the equational theory of the language. So they're imposed at the level of definitional equations or judgmental equations, depending on what notation you use. And then the language, the Fossak's calculus will also be extended with a further thing that I'll come back to later, which will allow us to define these handling constructs as a derived principle. So we're not taking these handling things as a primitive, but rather they are going to be derivable. On one hand, you have the handling construct that I showed you before, where operation terms will be redefined as computation terms, but you also can define a sort of a value version of it, where you take a computation and handle it into a pure value. And this is the style of handlers that I'm going to use in the examples. And the only difference here really is that operation terms are translated into value terms, and the continuation that you would call afterwards is also a value. So this is sort of in the pure Martin-Löf type theory fragment. Okay, so going on to the second main bullet point of the talk is, so if we have this calculus that has now both algebraic effects and handlers in it, so what can we gain from it? So on one hand, you can get this sort of additive composition that, okay, we can do our usual effectful programming with handlers, but with our value types just being slightly more detailed. So you can use dependent types to talk with value types. But the main kind of highlight of this paper is about another aspect of handlers and their usefulness, is that you can also use them to actually define predicates and reason about the computations. So this sort of bridges the gap a bit that you'll have you have effectful computations in language, but you would also like to reason about them. In many ways, you don't want to have a separate logic on the side if you already have dependent types and all the power of them. So you would like to do it in the same calculus, and that's what I'm going to show you in this sort of bullet point. So yeah, they're useful for this notion of extrinsic reasoning, in the sense that I'm going to the types of the computations are not very expressive, but there are going to be predicates on the side that are that are defined using the handlers that will describe the specifications of your programs that you're interested in. So yeah, the idea is that we're looking at computations that will return some values of some type A, and we want to define predicates over them, or predicates over thunks of them, because types can only depend on values in this setting. So essentially, all the examples that I'm going to show you in a few moments are follow a two-step procedure. So first of all, you define a handler on the universe or on your propositions, and then you just use the handling construct to go from your computations to the universe. Intuitively, you should think of the examples that you'll see in a few moments as kind of a computational procedure, that every such predicate takes a computation and churns through it and produces you a proof obligation that you have to give a witness to in order to show that your computation satisfies the property that you're interested in. There is another kind of class of examples that you could consider, which is not discussed in this paper, but essentially you could also use the handlers to sort of mimic monadic reification, and then use that to, say, do relational reasoning. So those who visited CPP on Monday saw a reification-based relational reasoning work done in F star. So in many ways, if you have handlers in your language, you can do the same thing as there. So you can go and look at that paper if you're interested. But yeah, let's now go on to the three examples of defining predicates using handlers. So first of all, it's sort of a very natural thing that you would like to do is say that I'm given predicates and return values, and I would like to lift them to computations in a somewhat a free way. So in this sort of handler-based setting, you can do it in a very natural way. So what we have is, we have a predicate and return values, and we want to turn it into a predicate and computations. I'm deliberately writing a box there. You'll see why that box is the natural thing to write there. And as I said, what we are really going to do is we're just going to use the handling construct with a particular user-defined algebra to go from UF of A into the type U. And what this handler or algebra is doing, it's replacing operations with essentially a universal quantification over the possible return values that they can produce. So the read operation that usually binds a value of type character and then calls a continuation gets turned into a universal quantification over the characters, and then the rest of the property. And the idea here is that the box P will hold of a computation if all of the possible return values will hold of the given predicate. So if you look at the equation down here, then this is sort of an example of what's happening. That if I look at box B at the computation, read followed by a write, and then returning a value, then if I apply box B to this computation, then this is going to be definitionally equal to universally quantifying over all the possible values that I can branch on. These are the possible values that the environment could give me. And for all of such values, the return value has to satisfy the predicate. So it's naturally a necessity modality in the sense of evaluation logic. And if I would like to get a possibility modality, a diamond P out of it, I really have to only replace the pi with the sigma, and you get the corresponding behavior. So the second example is, in some ways, in the same style. We're still kind of lifting predicates from return values to computations, but instead of considering an effect that doesn't have any equations in it, like the IO in the previous example, we're now going to consider the classical example of an effect that has equations attached to it, which is state. So one thing to notice there is that we can't do the exact same thing that we did before, because we can't just equip the universe with a sufficient handler, because the pi and sigma types that we could use, they don't satisfy the equations. So the actual natural thing that you will do then is, well, it's what's on the slide. So instead of taking a predicate and just return values, we take a predicate on return values and final states, so a post condition, and the predicate that we define turns it into a predicate on computations and initial states. And deliberately, it's being written WP. You'll get weakest preconditions out. And at the very high level, the idea is the following. So we take the computation that we're given here. We handle it as a state passing function in the usual standard sense. We'll feed in the initial state into the function, and then we project out the proposition. So it's kind of a stateful predicate that, again, takes your computation, does a bit of computation, and produces you a proof obligation. And then, yeah, you can show that this the WP of Q really satisfies the same the expected equations that you would expect from a weakest precondition. So, for example, the weakest precondition of put is the same as weakest precondition of the continuation, but with initial state altered with the value that you were putting in there. And then there's a third example, which is sort of in the style of session types in many ways, that when I have I/O computations, I can also talk about patterns of those. So I can kind of assume or define an inductive type of so-called protocols that essentially just saying that E says that it's end of protocol, R says that it's the read is the next action, and then W says the same for write. And then I can define essentially a relation between computations and protocols, which holds if the computation adheres to the corresponding protocol. And the idea is to define a handler on this function type where essentially what you're mapping an operation to depends on now what the protocol is. So if the protocol starts with the corresponding operation, then you essentially do what we did before. You quantify over the return values. But if it doesn't start with a corresponding operation, you just give back false. And then now just the last few slides about sort of giving a sketch of how this, what are the formalities between the extension of the calculus where the previous examples are doable. So we assume that we have algebraic effects around. As I said before, the operations will determine commutation terms. One of the main equations that you're interested in is this, which says that these so-called homomorphism terms are really homomorphisms, so they commute with operations. The key thing here is that the commutation kind of depends on what the type of K is. So it takes C operations to D operations. And then secondly, we extend it with a support for handlers. So you can sort of, an attempt one would involve, you could try the usual story of having this term level definition as we did before. So you could extend the computation terms with this handling construct. Now, as I said, we have these homomorphism terms, and intuitively also the handling is interpreted as a homomorphism. So you could also think of throwing a handling construct into the homomorphism land. Sadly, this leads you to an unsound system. Writing A and writing Z will become equal, which is definitely what you don't want to have. At very high level, it's Well, the problem is that the interaction between this case, as on the previous slide, was dependent on types, but the type of the handling construct doesn't really mention the handler in any way. Semantically, the handling construct is just interpreted as a carrier of homomorphism, not the proper homomorphism itself. So there are two ways to proceed. You could change the underlying calculus and have a system where homomorphism terms are not homomorphisms anymore, or you could think of a slightly different extension, which would have the feature, well, in which homomorphism terms would still be homomorphisms, but you would have handlers, but not the unsoundness issue. And this is sort of the second option that's followed in this paper. And the idea is sort of very simple. We're just stealing the sort of semantic structures in the sense that we are extending our computation types with a notion of an algebra, and from that notion we can just derive the handling construct, both for the computations and both for the value part. And the trick is just temporarily moving into this user-defined algebra type and then using just sequential composition and then using trunking and forcing to go back into C. And so that's the conclusion slide. So I hope you got at least some ideas that if you're in a dependent type language and you have effects around, then it might make sense to also consider handlers, because they help you to reason about your computations in a natural way, and you can give a nice type-based treatment of them. So thank you.
So questions?
So thank you for your talk. I have two questions. First, do I understand you correctly and you extend the type system to get your effect handlers in there?
Yes, so
Then my second question would be, what is the advantage of making that design decision compared to just using an just using a dependent type system, which, for example, Edwin Brady does in his effect handler implementation?
Okay, so answer to the first question is yes, I'm extending the computation types with this notion of user-defined algebra type, which internalizes the idea of a handler as an algebra. The answer to the second question is that I could do the same thing in a language very similar to this, in the style of Edwin Brady, of including essentially these handlers as something primitive. But because I have this computational sigma type and I have the first-class notion of homomorphisms, then in order to extend the calculus in a uniform way, I don't want to do this primitive extension, because then you'll have some of the interaction between operations and computation terms. So for some of the terms, it's described using this general equation scheme that I showed you. But for handlers, you would have specific equations talking about them. And I don't want that mismatch.
What kind of models have you considered so far? Have you also done something with local state?
So I haven't done local state in this setting. So the effects in this calculus have been global. And the kind of models I've been considering are essentially based on families fibrations and taking the notion of fibered effect theory that I have and turning it into expanding it into a Laverre theory, and then using families of models of Laverre theories for the computational side.
Okay, so we have an online question which says, how do identity types behave in the presence of effects? Are they defined just on value types, or are there identity types for computation types as well? And then they say, I'm thinking about Paul Levy's contextual isomorphisms work.
Okay, so in this calculus, identity types are just defined on values. If you want to have used identity types on computations, you would have to be using them on the functs of computations. That's essentially what's happening.
Any more questions? We have time for one more question.
Does your calculus actually improve the expressivity of the underlying dependent type theory? Or could you express everything here maybe in a syntactically much more heavyweight way in, say, Coq?
If you would do everything propositionally and sort of embed it deeply in Coq, I think you could do it, but you would, in order to, so we have these homomorphism terms, in order to kind of guarantee the linearity properties that you get there, I think the one way to go about it is to consider computation terms with specific equational proof obligations rather than the specific class of terms. And if you do that, you get much more closer to being able to do it in an underlying type theory.
So, in particular, you get more judgmental equalities. Is that right?
Can you repeat the question?
You would get more judgmental equalities.
I don't think so. We can discuss it offline.
Okay, yeah.
Okay, let's